All right, so we'll continue, starting with some terminology. Yeah, a lot of terminology, so you have to remember these things, okay, because it's very important. Without them, we cannot discuss things. All right, so let's start with some very basic terminologies between edges and vertices. So suppose we have an edge, so E is an edge, it's a pair of unordered pair of distinct vertices. So it's between U and V, all right? So formally, we should write edges will be represented by UV. As a set, it's unordered. But very often we just use UV or VU. UV and VU are same. But for undirected graph, these two are same. They call relation symmetric relation. Okay. So normally we use UV or VU. So alphabetically UV, typically UV, depends on how. So usually from left to right, maybe. Okay, because way of how we write it. So we say that this edge E connects these two vertices, U and V or V and U, joins these two vertices. And these two vertices are adjacent. We can say U is adjacent to V or V is adjacent to U. Then U is a neighbor of V and V is a neighbor of U. All right, so these are very natural terms. And in terms of relation between edge and vertices, we say E is incident with, is not to, incident, not incident to. Sometimes people say incident to, but it should be incident with. E is incident with U and V. And of course, these two vertices are said to be incident with edge E. And then these two vertices are endpoints of E, or end vertices of E. So very natural, right? When we talk about relation between two edges, if two vertices, two edges share common vertex, we say these two edges are adjacent, right? So let's describe the relation between edges and vertices, edges and edges. There are of course other relations. Later on, when we need them, we'll introduce them. All right. For the time being, these are very basic definitions and terms in terms of connection between vertices and edges. All right. Okay. That should be very clear, right? Similar to diagrams, for vertex, we can have its neighborhood. We can have its neighborhood. So there's a set of neighbors. The neighborhood, this one is a set of neighbors. Of course. So these are vertices adjacent to V. The neighborhood will contain these vertices. So here, because edge has no direction, so we don't have in neighbor, out neighbor, just neighborhood or neighbors. Right? So that's the neighbors of V. The vertices adjacent to V. So this one, in terms of set, we can write in this way. Sorry, I maybe like U is adjacent to V. If I use V already, set of vertices adjacent to this particular vertex V. All right. So then the degree, again, we can have definition of degree. So we don't have in neighbor, out neighbor. So we just have degree of a vertex. In short, we just say degree D of V. Sometimes D may refer to distance. Very often it refers to degree. It should be clear from context. So if it's called confusion, use DEG. Otherwise, one can use D of V. All right. So that's in short. So that's equal number of edges incident with V. Okay. So since it's a simple graph, the graph is simple, so means no multiple edges. The graph we discussed is also called a simple graph, so means no multiple edges or parallel edges, and then no loops. All right. So then this one degree is exactly the size of its neighborhood. So this one holds. Now it's important. This one holds when they have no loops. If there are loops, we define degree. For example, look at this one. What's the degree of this vertex? Whether it is 3 or 4. All right. So if we use this one, it gives us 3. So actually, this one should be 4 because there's 4 lines connected with this one. So it should be 4 instead of 3. So we cannot just simply say in this way. If there are loop, degree will be counted as 2. But luckily, usually we don't deal with loops. So does not matter. Okay. So remember, no loops. So this one I will hold. All right. So let's see what else we need for the basic thing. Oh yeah, computer representation. Yeah, I just briefly tell you the 2 representations. In algorithm of the structure course, these things will be discussed. Okay, computer representation. So there are at least 2 ways. One is adjacency matrix. One is adjacency list. One is to use a matrix to represent the graph. So instead of drawing the graph, we cannot do it in this way for computer. For example, this graph. We cannot use this one as input to the computer. Computer cannot tell. Now that maybe with AI it's okay, but usually that's not the right way to feed it to a computer. So we can use a matrix to represent this graph called adjacent matrix. Let's see what I use. Use adjacent matrix. I use A. An n by n matrix, zero one matrix. This one zero one matrix, where AI is 1 or 0. So basically, that's how we represent binary relation. So that's how we use the other one matrix to represent binary relation. So we have vertex set. We assume it's B1, B2, B. Okay. So for this one, it will be 4 by 4 matrix. All right. It's symmetric. The matrix will be symmetric. So here, diagonal, because no loops, it will be all 0. 1 is adjacent 1 and 2 and 4. So this is adjacent to 2 and 4. So this one is 0. 2 is adjacent to 1 and 4. So 0, 1, 1. So triangle look like this, and it actually is symmetric. So that's adjacent matrix representation. All right. Some of them you may know already if you have done programming course. Yeah, I think you should know this, right? In programming course, it may have been taught already. Adjacent list for each vertex, we list its neighbors. For each vertex, we have its neighbor, list of its neighbors. So for example, B1, for this vertex B1, its neighbors will be B2, B4. We listed it. For B2, it's B1, B4. B3 is B4, and B4 is B1, B2, B3. All right, so that's called adjacent list representation. These are two very basic representations for a graph. Later on in algorithm course, we'll touch these one in maybe in a little bit more details. Exactly different representation for this one. Depends on the application. Sometimes we may add them, sometimes we may not. Sometimes we may use link. It can be quite complicated. All right, but this one is quite obvious, it's straightforward. CL1 matrix. All right. Okay. Let's see if there are questions. Oh, okay. Yeah. Thanks. Thanks for telling that. Programming costs cannot give. Haven't discussed these representations. I will not get into details because these are really things for data structure and algorithm cost. But just give you an idea, we can use this to represent a graph, or this one to represent a graph. There are other ways, incidence matrix, for example. Okay. So an idea would be good enough. We cannot use this one as input. We need to use a matrix or a list. All right. So we're not getting into detail because it's not algorithm cost. Okay. All right. I think that's enough for the basic terminology. Let's see what else to understand. Oh no. Okay. Good. Now we'll discuss something basic property of a graph. So we can discuss the things about the graphs with these basic technology. Other terminology, not technology. So focus on a graph, undirected graph. Okay, so we focus on undirected graph, but not high graph. All right. So there are some basic properties. First is the maximum number of edges. How many edges can we have in a graph? Maximum number of edges in a graph. How many? Per graph. In this case, we can also consider what's the maximum number of edges on high graph. So very basic counting. Okay, how many for high graph? It's a binary relation, right? For binary relation. In a high graph, every pair is possible. Total number of pairs, there are n choice for the first element, n choice for second element. So for high graph, n squared for diagram. Now for graph, it's an ordered pair, and we don't have loops. So how many? Once we choose, first we have n choices. First element, so each edge is a pair. Each edge is a pair. UV is a pair, right? So it's a pair. It's an ordered pair. So of course, it's C choose n choose 2. So it's C and 2. It's a distinct element. Pair of distinct element, and it's unordered. So choose two elements from n, so which is n minus 1, 2. So that's the maximum number of edges. So that's a very, very basic property. All right. So what does it mean? The number of edges can grow quadratically. So in terms of number of vertices, number of edges can be in the order of n squared. So it's about always ordered about by number of square of number of vertices. All right. So it's quadratic, but no worse than this one. All right. So this is very, very, very basic. Second one is what's the summation of degrees? So we need to do something with the degree sums. All right. Now here I will also consider line graph, maybe because it's very simple. B. for diagram, summation of in degree will be same as summation of outer degree. It's very easy to see because for each edge, it will be counted once from this end and counted once from this end. So this one as outer degree, so this side as outer degree, this side of as in degree. Of course, when we have in degree equal outer degree for diagram, you can count twice. Once in not for this vertex, it's outer degree. For this vertex, it's in degree. So the counted one on this side, counted one this side for each edge. All right. Now for undirected graph, for graph, this summation counted an edge. It's counted once on this side and counted once on this side. For each edge, it counts twice. One from U side and one from E side. Therefore, this summation is twice number of edges. Okay. So let's take a very simple example. For example, again, this graph. So this 1, 3, 2, 2. Its summation is 8. So number of edges is 4. So it's summation of degree sum is twice the number of edges. This is very important. It's also called handshaking theorem. So total number of people, number of times people shake hands in a party is always an even number. All right. Later on, it will give us a useful theorem. So this one looks to be very simple, but it does imply a very important result. Let's see. All right, it's trivial, but it implies the following important basic property of a graph. So called corollary. So in a graph, some vertex may have odd degrees, some may have even degrees. So degree 3 is odd. So this one is even. All right. So in this possible, we have a graph. It looks like this. So this one is odd, this one is odd, and all other vertices have even degree. Is it possible to have such a graph? Spawning corollary actually will tell us actually this one is impossible. Okay, let's see. No, this is not alternated. Okay, sorry. No, it's this one is possible. So I mean, what do I mean? No, this one is impossible. Forget about this one. This one is possible. Okay. I have something else in mind. I will discuss this one later when I talk about class. Okay. This one is possible. Sorry. Okay. So some vertex may have even degree, some vertex may have odd degree. So from here, we can say the number of all the vertices in any graph is even. So if all right, the vertex is called odd vertex if its degree is odd, even vertex if its degree is even. So in this also we have say a graph on 9 vertices, where each vertex has degree 3. So is it possible? Can you construct such a graph? So this result tells us no such graph exists. this one the number of all the degree vertices must be even. So here we want 9 vertices of degree odd. It is impossible. Okay. The proof actually is very simple. Let me just have a simple one. For multi-block, can we number of parallel edges that one is connected? I don't quite understand what you ask, whether you mean they are connected together or not. I will come back to you later, okay, because I'm not quite sure what you meant. Okay. Uh, okay, so this one actually is quite simple. Let's see notation. So by this one, what we have, we classify graph into 2 catalogs. So here, summation of degree. So this one can be break down into 2 parts, odd versus even versus. All right. Now, by this theorem, the summation is even, equal to n. Okay. Now, this even, every number here is even. So this summation here is always even. Now, this number is odd. So in order for this part to be even, sum of all the numbers, in order for sum of all the numbers to be even, the number here must be even. So that's how we get it. Number of vertices is even. So that's a very simple fact. Another fact is another very basic part of fact is every graph has 2 vertices of same degree. Every graph with at least 2 vertices always contain 2 vertices of same degree. Does this one still remember this one? Actually, we already did the graph theory. This question is it 5? I think in homework 3. So actually, it's a graph theory. All right. So here we can just talk about degree of the graph. The same degrees, because range of degree is from 0 to n minus 1. Range of degree of vertex from 0 to n minus 1. So when we have, it's in the homework. I think tutor may discuss the solution already. So we have n vertices, degree is from n0 to n minus 1. We can use pigeonhole principle, but we cannot use it directly because directly it's a major pattern. N pigeon here, there are n boxes, n from 0 to n minus 1. All right. So we have divided into 2 cases. One is there are isolated vertex. Another one will not isolated vertex. Then situation becomes value will be between 1 to n minus 1. So n into n minus 1 boxes, 2 will be have the same value. All right. So another case if one vertex is isolated. A vertex at degree 0 is called isolated vertex. If it's not adjacent to any other vertices, it's called isolated vertex. All right. So we may have isolated vertex. The graph may have one isolated vertex and rest is here. Now for vertex inside here, the degree will be from 1 to this one. Of course, yes, if there are another isolated vertex, then Z2 will have same degree 0. Otherwise, degree here will be from 1 to n minus 1. But number of vertices here is n minus 1. So by pigeonhole principle, 2 will have same degree. So actually, you did it already. So we haven't touched graph theory. That problem really is a graph theory problem. It's a graph problem. Right? Okay? This deep graph really come everywhere. Then there are some important graph, basic graphs. I will want to give you notation on these basic graphs, special graphs. There are a few of them. Um, the first one is a so-called complete graph. That's the most dense graph. It's called complete graph. So K1 is a vertex, is a graph with a single edge. K2, two vertices with an edge between them. K3 is going to look like triangle. So it's all possible edges. All right. So K4 will be four vertices. This one, or we can draw it in this way. So that's K4. So it has exactly n times n minus 1 divided by 2, this many edges. The graph contains most number of edges on n vertices. Such a graph is called a complete graph. All right. And sometimes we have the vertex that can be partitioned into two parts. When we talk about relation from A to B, so these two are different sets. Then the graphic representation is one side A, one side B. There are no connection between elements inside A, no connection between elements inside B, only connection from A to B. So this kind of graph, the only edges look like this. All right, such a graph is called a bitype graph. This is a very important class of graphs. We'll discuss more later on. Okay. So for such a graph, we can also have so-called complete bitype graph. So there's a bitype graph. One side has P vertices, another side has Q vertices. And we have all possible edges cross A and B. So all edges cross A and B. So this denotes this kind of graph, bitype graph. So K11 is one vertex on this side, one vertex on this side, the edge connected. So that's the same as K2. All right. So K22, we have two vertices on this side, two vertices on this side, so we have all possible edges. And the K23, the two vertices on one side, three vertices on this side. So we have situation like this. These are complete bitype graphs. In particular, K1T, one vertex here, T vertices here. This one is also called a star. Because if we draw it in this way, so it looks like a star. So these are rays, ray of star. Okay, so that's called star. That's complete bitype graph. So one side has P vertices, another side they have Q vertices. So total number of edges is P times Q. Number of edges exactly equal to P times Q. All right. Two more special type of graphs. Very simple structure. Paths and cycles. A cycle of n vertices is called a cycle because it looks like cycle. The smallest cycle actually is with 3 vertices, C3. If we allow loops, then the C, but it's not regarded as cycle C1. If we allow multiple edges, we have this icon, we can call C2, but usually we don't allow them. So these are not really allowed. Depend if you, but usually we don't use them. But if you in your application you need them, you may call this one C1, this one C2. All right. Usually it starts with C3. So it's a 3 cycle. Then we have 4 cycles, C4, so 4 vertices, and C5, and so on. All right. The paths is a path, it really look like paths. So P1, P1, that's P2, sorry, start from P1 is a single vertex. Maybe I should start with P1. P1 is a single vertex, P2, a vertex on two, an edge between 2, and the P3, so 3 vertices. So this one with 1 edge, this one with 2 edge, P4. All right. So that's part in the cycle. Very, very simple. So these are very basic graphs. So if we delete a vertex from cycle, we get a path. If we delete it, we get a path. If we identify 2 ends of a path, we get a cycle. If these 2 vertices are merged together, then we get a cycle. So connection between path and cycle are very close. Yeah. All right. So what else we need? Maybe I use complement first. Yeah, complement. Okay, so if I use this one to denote its complement graph, so this one is the original graph, then vertex set will be same. So this one, its vertex set is exactly the same as B. Okay, but edge set, it just contains edges that's not inside E. The UV is an edge of E if only UV not an edge of E. That's called complement. So this really comes from the complementary relation. But yeah, be careful, symmetric relation and loops. Some of these small technical things, so we cannot really say it's complementary relation. But basically, it's from complementary relation. So in the other one matrix, complementary graph, let's see, maybe this one again. 1, 2, 3, 4. So look at adjacent matrix. The diagonal is this one. So 1 adjacent to 2, 2 adjacent to 3 and 4, and 1, 3. In adjacent matrix, what happens is it's a graph we have adjacent matrix. Just turn 1 to 0, 0 to 1, except the diagonal. Diagonal remains 0. So its adjacent matrix will be diagonal, remain unchanged. Because always symmetric relation. Right? Now the intrigue 0 become 1, 1 becomes 0. That's the complementary graph. So in this one, red one represents edge in the complement. So graph look like this. So the complement is this graph. That's the complement of this graph. Red one is the complement. So red one is the original graph. Red one is its complement. All right. So that's complement. It's very easy. If edge not in the graph, in the complement is always there. So some graph, for example, this one, the complement of this graph is this graph. The complement of this graph look like this. This is complement. Okay. So let's look into this one again. Okay. So we have G here and the complement here. The question is, these two same graph are different graph. Of course, they're different, right, in the drawing. And because the label, if we look at the label, so 5 adjacent 2 and 3, here adjacent to 1 and 4. Of course, they're different graph. But in terms of structure, these two same graph are different graph. So what do we mean by the same analysis? So this one, if I draw it this way, so they look different from that one. But if I draw it this way, this graph and pull 5 over, and then it's drawing to look like this. Then these two graphs, this one and this one the same, of course, still look different. All right. But now if this one, I draw it in this way, so I pull 3 over here, then it look like this. Then I ask the same question, are these two graphs same graph? Of course they're different because the one adjacent to 3 and 4. Here one adjacent to 2 and 5. But do they actually look something similar? They have similar structure? Actually, yes, right? Both of them representing C5. So all of them are actually different drawings of C5. The only difference are just labelings. If we ignore the labels, ignore name of vertices, ignore them, then actually they represent the same graph. So these are just different drawings of C5, right? So the natural question is, how do we know whether two graphs have same structure or not? Sometimes, if they have same structure, so results for this graph can be applied to this one. Just labeling is different. We just change the names. So every result here can be transformed to result in this graph. So it's very important to see whether two graphs are same or not. The same or not. Okay. So that's bring us the notion of graph isomorphism. Isomorphism means same structure. Mathematically, it means same structure or similar. Okay, whether two graphs are same or not. All right. So really, we are looking to whether two graphs are same or not. They're just different joins or structurally they're totally different. So for example, let's look at a few more examples. So I'm asking the same question. Are these two graphs really same graph or different graph? Or same graph with different labeling? So that means that structure thing, just name are different, or they're just really different graphs. So actually you can easily see that for four vertices, the maximum number of edges will be six. All of them have six edges. So they are complete graph on four vertices. So they are really same graph. It's K4, but you will use different labelings. All right. Now if I remove their names, these should have exactly the same structure. The structure is same, just a different ways of drawing. So for this one, if I pull this one over here, so if I move this one to here, then I get exactly this graph. So really they have the same structure. All right. So let me give you one more, two more example. Um, okay, now I have two different graphs. Of course, they look differently. Even name are different. A1 here, A1 to A6 here, B1 to B6. But do they have the same structure? So if you look carefully about this graph, if I put these two inside and rotate it 90 degrees, I get that graph. If I put both of them inside, then rotate it 90 degrees, I get exactly that graph. But how can you convince me or tell me that these two graphs have exactly the same structure? One way one can do is give correspondence of vertices. So you can tell me actually there are correspondence of vertices. So AI corresponding to BI. And this correspondence actually they say exactly the same. So what we mean is there are correspondence between vertices so that in the adjacency of vertices are same for these two graphs. So that's how the notion of isomorphism comes from. So let me give you a definition, then stop. Okay. So I have two different graphs. And when say these two graphs are isomorphic, means they have same structure. So mathematically, that's how we define two structures same. So there are one-to-one correspondence. So that's one-to-one correspondence by direction. So like A1 corresponding to B1, A2 corresponding to B2. So whenever A1, A2 say is an edge, here is image. So this edge corresponding to this edge. Whenever you be an edge, then its image form an edge. That's called the same structure. So for this one, A is adjacent to 2, 4, 5, adjacent to these three. So here we're adjacent to B, C3 vertices. So they really have exactly the same structure. So in object representation, that means there are another way of drawing this one, and it's not exactly same as this one. Okay, I think I get up now. It's a good exercise. Find the isomorphism between the two graphs I given uh, in the very beginning of the lecture, also in the notes. These two graphs, these two are different drawings. These two are different drawings. A very famous Peterson graph. Try to find the isomorphism between these two. Actually, it's not difficult at all. So once you find it, you will have a better understanding of the notion of isomorphism. All right. So I will stop here and then continue on Wednesday. The submission of homework form will be open in a few minutes. I'll work on it. I need to change something. All right. So see you on Wednesday. Okay. Oh, by the way, the average mark for midterm should be close to 70. Should be very close to my random sampling. So still really made a mistake. They thought the Q4, I think it's Q4, total mark is 3. Somehow they did not look into the total marks. They thought it's 3, actually it should be 5. So everyone, most of you should get 1 or 2 marks more, I think. Okay. So I asked here to correct them. I haven't received their file yet. I will ask them again. Okay. Thank you. Oh, yes, that's what you number about the edges in the matrix representation, of course. Yeah.